Hey, in this video we're going to talk about a special kind of subatomic particle called a neutrino and how neutrinos actually serve as messengers coming straight to us from the center of the sun. But first, a quick review. We've talked about the sun, and I've given some very specific numbers about and very specific descriptions of the structure of the sun. We have this radiative zone, we have the convective zone, the core, the temperature, the million at the center of the core, 15.7 million Kelvin. Very specific numbers, very specific numbers. And we've talked about the proton-proton chain, this nuclear reaction that's actually a series of several steps that has the net result that it takes 4 hydrogen nuclei, in other words, protons, 4 hydrogen nuclei and convert them into a helium nucleus. And that's the ultimate source of the energy of the sun. And so we talked about the proton-proton cycle, we talked about the structure, radiative, convective zone, even these graphs of density as a function of the radius from the center and temperature as a function of the radius, very detailed claims about our understanding of the structure of the sun. So how the heck do we know? How do we know that all of this is true? Well, one way is through numerical models. Remember, numerical model is another way of saying a computer simulation. And so you can build a computer simulation, computer code, that will predict, for instance, the power output of the sun, as well as even the spectral lines. You know, in the spectrum of the sun, there are literally millions of those absorption lines, and we can account for almost all of them. Now, when you code a simulation, in that simulation, it's basically a series of calculations that are being done over and over again as you simulate time going forward in small little steps. And so what are the physics principles that get incorporated into that? Hydrostatic equilibrium. Remember, that's basically a liquid with gravity pulling down on it. The pressure gets more the deeper down you go. Like you go swimming in a pool, you dive down, the pressure is greater. The electromagnetic interactions between charged particles. What's called the strong force. The strong force is the force that holds nuclei together. When you think about protons in a nucleus, well, they're positive and positive, right? Protons are positive. Shouldn't they be repelling each other? They do through the electromagnetic force, but there's also this so-called strong nuclear force that is stronger than the electromagnetic and holds the nucleus together. We know how that works, and that can get incorporated into the computer simulation codes. Fluid dynamics, the physics behind turbulence. And then also quantum mechanics, which is a whole nother ball of wax, but an area, nonetheless, a field of physics that we understand pretty well. And then also relativistic effects, having to do with the conversion between mass and energy. And then also the interaction between photons, that is light waves or light particles, and charged particles. So the fact that our computer simulations incorporate all these bits of physics, and then when you run that simulation, it correctly predicts the power output of the sun and the spectral lines, that gives us confidence that we know what we're talking about. Now, another piece of evidence that gives us confidence is that we have a special kind of telescope called a neutrino telescope that sees neutrinos that should be coming, by our understanding, that should be coming from the center of the sun. We actually do see them. And so that gives us confidence. And that's the main point of this video, is to talk about neutrinos. I will mention there's also a field of studying of the sun called helioseismology, basically looking at the vibrations of the sun and the surface of the sun to determine what's going on inside. That's kind of cool, but that's a separate topic. So Let's talk about neutrinos. First, what the heck are neutrinos? They are extremely low mass particles with no charge. Way less mass than an electron even. And neutrino is actually Italian. It means little neutral one. So they have no charge, and the eno part, it means they're small. And they're extremely small. They have mass, but it's just way, way, way less than an electron. And a particular kind of neutrino is predicted to be produced in the first step of the proton-proton cycle. So the proton-proton cycle, we've talked about that. Step 1, two protons collide. One of those protons turns into a neutron. And a couple things come off from that. First off, you get what's called a positron, basically an electron with a positive charge. And is called a positron. And then this is a little neutrino. Now the thing about neutrinos is that they interact hardly at all with matter. They have no charge. They have very little mass. And they interact with matter only with what's called the weak nuclear force. And so neutrinos can just pass through the entire Earth, and the odds are it's not going to hit anything. And so why is that property important? Well, here's another kind of cutaway diagram of the sun, with the core being where the nuclear reactions are taking place. The whole proton-proton cycle is happening here in the core. Photons, they start as gamma rays because the temperature is so high, but photons, the electromagnetic radiation, takes a couple 100,000 years to get out because photons interact with the charged particles very, very strongly. So a photon that's wiggling will hit, a proton or electron and basically be scattered in a random direction, and then immediately go and hit another one, and hit another one, and hit another one. It's kind of like if you were at a big rave and you were trying to you weren't dancing, you just wanted to walk across the dance floor. But everyone is raving, everyone's just running around like crazy, and you're trying to go in a straight line. You're going to be buffeted every which way. So the photons, the electromagnetic radiation created in the center of the sun, actually takes a couple 100,000 years to make its way out. Whereas neutrinos, they travel basically at the speed of light, and so they'll go from the center of the sun to the surface in a couple seconds at the speed of light, and they'll get to the Earth in 8 minutes at the speed of light. And this is what I mean by neutrinos are a direct messenger, coming to us straight from the core without being held up, without being delayed. And so how do we know this? How do we detect these neutrinos? Well, this is what's called a photomultiplier tube. It's a big one, but it's one of thousands used in a neutrino detector called Super K, and in Japan. Now, there are several of these neutrino detectors around the world. This isn't the only one. But the numerical models, the calculations of how many of those proton-proton reactions are happening per second in the sun, and then how far we are away from the sun. If you do those, it's just massive numbers. It's hard to wrap your head around these numbers. That you, assuming you're an average-sized human being, there are 10 to the 11 neutrinos passing through you every second. Let me be careful here. Through every square centimeter of you per second. So 10 to the 11, that is 100 billion. So there are 100 billion neutrinos passing through every square centimeter of you every second, coming from the center of the sun. That's just, it's a mind-boggling thought. But the vast majority of them never interact. In fact, the vast majority of them go through the entire Earth and never interact, never hit an atom, hit a nucleus, or do anything. And I've already mentioned this, they interact very, very weakly. There are only four forces in nature: electromagnetism, the strong and weak nuclear forces, and gravity. And the weak nuclear force is weak. And so these particles hardly interact at all. So most of these neutrino detectors around the world, like I said, there are several of them, use water. And when a neutrino hits the nucleus of the hits a proton in the nucleus, converts it into a neutron, you'll get a little flash, a little flash of light when that happens. Again, the vast majority of neutrinos don't do that, so in order to increase the odds of seeing any of these little flashes, you have huge amounts of water. And this is the inside of the Super K detector in Japan. And this previous picture here, this photomultiplier tube, is one of these things on the wall. And you see that's a boat. That's a boat with two technicians in it. And they're floating in the water. So the tank is only partway filled. And what they're doing is they're doing maintenance on some of these photomultiplier tubes. So the way they do that is that they actually lower the water to the level of the photomultiplier tube they need to work on, and then they have a boat. And they go out there and they do whatever maintenance work that they need to do. And but when they're operating it, they fill it up so that this whole spherical tank is full of water. And then all of those thousands of photomultiplier tubes are looking into this dark spherical ball of water, looking for a little flash of light coming from a neutrino that happens to cause a beta decay in the nucleus of one of those water molecules. And so the Super K is 40 meters in diameter, 50,000 tons of water, 13,000 of these photomultiplier tubes. And they get a couple dozen detections per day. So, but that is exactly what they predict. That is the physics of the weak nuclear force and the interaction of the neutrinos with the molecules, the predicted flux, that is how many are coming through, the chances of any one of them. This is in fact exactly in line with what should be expected. So that is one of the reasons that we feel confident that we know really what's going on in the very center of the sun, because neutrinos are messengers confirming our understanding.